Okay, we will now do section 10.2, which deals with two sample t inferences, two sample t intervals for the difference in means, and two sample t tests for the difference in means. And so here we go. So we're going to look at a context and a sampling distribution. The concept of it is the basis for which the theory behind our mechanics, behind creating these confidence intervals and finding the test statistic p-values are based upon the concept of a sampling distribution. So understanding what a sampling distribution is one of the more confusing things a lot of times for students. So it may take some work to understand that. But so here we go. It says a farmer wishes to estimate the mean, to estimate the difference. And so that's kind of the big word in chapter 10, that it's the difference in something. The difference in the mean. So that's telling you chapter 10. That's telling you chapter 10, section 2. So we're going to be doing, of course, who's mean, Mr. T. And so we're going to be doing t intervals and t tests in this section. The mean weight of his potatoes from his north field and the mean weight of his potatoes in his south field. Unbeknownst to him, the mean weight of the potatoes in the north field is 22. So that's all the potatoes. So that is a parameter. That is mu. Okay, not x bar. All right, with a standard deviation of 4. That is the standard deviation of all of the potatoes. So that is sigma. If it was a sample standard deviation, it'd be S. All right, and these are ounces. Make sure to include the units in this section. While the south field, they have a mean weight of 29 and 2. That mu and sigma, those are population values as well. All right, he takes a random sample of 50 potatoes from each of the two fields and finds the difference, which you don't have to have the same size sample. And every example that I'm doing in this chapter, I'm doing that, at least on these videos. So don't think that. You don't have to. It doesn't have to be the same sample size. But anyway, describe the sampling distribution. So what's happening here is we've got two populations now. We've got the north. In this chapter, we always have two populations. In other words, two groups of animals, people, animals, or things that you want to know something about. In this case, potatoes in the north field and potatoes in the south field. And so let's talk about the sampling distribution of the north field. In other words, every value that this sample mean could take, because he's taking a sample mean from each, he's finding a sample mean for each of the two fields. Well, in the north field, the average is in the north field, the mean is 22. So he's going to get an X bar. It will probably be somewhere around 22. Okay, but it won't be exactly equal to that, more than likely, because of sampling variability. If he were to take another sample of size 50, he would get another X bar. And then a third sample, you get a third X bar. And if you kept going and getting a large number of X bars, this is a sampling distribution, just as we talked about in Chapter 7. It's approximately normal because the sample size is bigger than 30. Because of the central limit theorem. Okay, and so of course the mean is 22. Now the standard deviation of these X bars, the standard deviation of the potatoes of the X values is going to be, let's see, 22 at standard deviation of 4, but it's going to be 4 divided by the square root of 50 for the X bars. When he's taking 50 values and averaging them, this isn't just one X, it's the average of 50 X's. And so when you do that, it's that. And of course, we learned that in Chapter 7. Okay, so then, in the south field, he's going to take a sample. These X bars, he's just getting one of them, mind you, but it's just one of many he could have gotten. This is all the possible ones. So he's going to get one of these X bars. We don't know which one, so I should call these X bars sub N for north and X bar sub S for south, let's say. They'll be approximately normal because of the central limit theorem, sample size bigger than 30. And then that is the mean, and then the standard deviation of these X bar sub south, and this is X bar sub north, is going to be equal to sigma over the square root of n. So that would be 2 over the square root of 50. Okay? And so that is a Chapter 7 concept. Now, Chapter 10 is this, he wants the sampling distribution of the difference in the sample means. So he's estimating N minus S, we will say, north minus south. So he is taking a sample, an X bar sub N, or X bar sub north, one of these X bars. And then he's subtracting a randomly selected one from here, X bar sub south. And what possible values could these take? All right, well, if we look at the difference in these things, in general, they're going to differ by 7 on average. So, but by sampling variability, it's probably, and I'll call this D, I'll call that difference D. This difference is going to be around 7, but not exactly equal to it because of sampling variability. He may get like 29.1 here, and then 21.1 here for, and of course that would, be a difference of like 8. Or get like 29.03 here and then 24.06 here, and it'd be a different difference. And if you took many different, he kept getting X bars here and X bars here and subtracting them again and again, he would get many different differences. Okay? These differences are what we call the sampling distribution of differences. They will be approximately normal because these two sampling distributions are approximately normal. And when you subtract two approximately normal distributions, the result is an approximately normal distribution. And their mean, you can just subtract the means. But we cannot subtract the variances, the standard deviations. And this goes back to chapter 6. All right, we have to add the variance. So the variance of these differences is going to be the sum of these two variances. And remember, the variance is the square of the standard deviation. So the variance of X bar sub n, I just square that, and that would be 16 over 50. And the variance of the X bar sub s is, I square that, and that's 4 over 50. And so when you subtract two random variables, to find the variability, you add the variances. And so this would be 16 over 50 plus 4 over 50, like that. And so our standard deviation actually would be the square root of those things. The standard deviation, I would just take the square root of both sides to be the square root of 16 over 50 plus 4 over 50. And if you look on your formula sheet at this section, the standard deviation, the two sample stuff, there it is. There's that formula, is the standard deviation of our statistic, which is going to be a difference of sample means, okay, is going to be this right there. And that is exactly what this is. And that, as it turns out, is equal to approximately 0.63246. So that is the standard. So if we were going to, it asks us to describe the distribution, so we have to cuss. Right? And so we would say, well, the center is 7. The center of the difference is 7 because that is the difference in the means. Okay? The unusual value, well, the shape is approximately normal because of the central limit theorem. Okay? It's approximately normal, and by saying it's approximately normal, that takes care of the outliers or unusual values as well. All right, because by saying it's approximately normal, it describes the nature of the outliers. And then you could say the spread is described by the standard deviation of 0.63246. Or you could say the variance, whatever it's equal to, which would be the square of that. But there you go. And so that is the concept of a sampling distribution. That is the theory that our mechanics is going to be based on. So I've got a couple of different examples for you in regards to making an interval and making a test. It's really similar to what we did in section 1 in regards to using the TAME and THAME acronym, TAME for an interval, THAME for a test. And so this says a consumer group wishes to compare the amount of mercury in water from a river near a chemical plant and the amount of mercury from water from another river that has no chemical plant. So that is two different, we are comparing two things. It is, so wishes, and so that, okay, so that tells you kind of chapter 10. We're comparing two different things. The group takes 50 samples of 6 ounces of water from the river near the chemical plant and 50 samples of 6 ounces of water from river that does not have the chemical plant. These samples can be considered random samples from their populations. Okay, so that is going to take care of one condition, certainly. And the samples from the first river have a mean. So I'm going to write this down. So I'm going to call this X bar. So I'm going to say, let's say C for chemical plant. So C for chemical plant. Let me remember that. Or you could just do X bar sub 1, by the way. but it has a mean of 124, and it has a standard deviation, S sub c, so its standard deviation is 14. And then the second river, that would be X bar, no chemical plant. That has a mean of 106 and a standard deviation of 21. So S sub n is going to be 21. Now, in regards to these things, we are going to consider this 50 samples of 6 ounces of water. We're going to consider that basically one sample of size 50 is in essence what that's trying to communicate. You're in essence, that's the way we're going to look at it. So our sample size for both of these is 50. So our N sub N is 50, and also our N sub C is equal to 50. Once again, your sample sizes don't have to be the same size, and I wish I hadn't have done that in every one of these examples, but it's okay. So they don't have to be the exact same sample size. So that is our stats that we have, in essence, we have going on here. So anyway, all right, so it asks us to create a 95% confidence interval for the difference in the means. So we want to now, so we're expecting, if you subtract these two things, all right, you would get 18. But these things are estimates of the population value. So in essence, what we're going to do is take that difference, go a little to the left and a little to the right, and say, we're 95% confident that the true difference of the mu's is actually in there. So that is in essence what we're doing. So here we go. So now we do our TAME acronym. So our type of inference. So our type of inference, and we are calling this thing a two-sample T interval, two-sample T interval for the difference in means. Or you could just say two-sample T interval for means. But this would be sort of the complete way. And it is means, not, say means, not, it's plural. So it's a bit cumbersome. It is what it is. And then we have our assumptions or our conditions, and we must verify them. So we must verify our assumptions. And this is just like the last section. It is I sin. When you have this two-sample, one-sample stuff is sin, like chapter 8 and chapter 9. But now it's I sin. We have to have an independent random sample or an independent SRSs. And so it says that they are random samples. Independence just means these samples are influencing each other or in any way, which there's no reason to believe that here, and you haven't had a paired design, like a match paired test. And we'll do examples of that later in the chapter. But anyway, we certainly have, there's no match pair design. They aren't influencing each other in any way. The vast majority of the time, you can just say, it says random samples were taken, so thus independent random conditions met. But you got to include that word independence here, not just this aspect of the word independence. So you would say, it says they are random samples. They're considered to be random samples. Thus, independent, don't leave out that word with the two samples. With the one sample, you don't say that. Thus, independent random condition is met. Condition is met. That's the easiest way to say it. Then this aspect of the word is, our population sizes. There's two of them. Don't just say n. There's more. There's two of them. Greater than or equal to 10 times our sample sizes. And so you would say here, there must be at least 500, samples like this, we will say, since that's the language they use, samples like this in each river for our population sizes to be at least 10 times our sample sizes. Okay, so, and that's certainly very reasonable here as far as a river goes. And then lastly, we have our normality. And so, and which will be very simple in this case, there's three things that could possibly establish normality. Number one, if your sample sizes, both of them, are bigger than 30, and they both are. So we got it here. Or if it's said up here that your populations vary approximately normally. It didn't say that. Or if you graph the sample data, and as long as you don't have outliers or strong skewness, you feel good about normality. But what we can say here is you could say, both sample sizes, both sample sizes equal to 50, which is greater than 30. So by CLT, central limit theorem, normality is met. Normality is met, or our sampling distribution of differences is approximately normal. In other words, this thing up here. All these possible differences between our sample means will be approximately normal, okay? So, but you can just say it like that. So you can just say, so that is that. We have I sin, okay? I sin, so that's good. And so now we do our mechanics, okay? So now, yes, you can use the shortcut on your calculator to create the mechanics. But you do need to understand, how to make this interval by hand. And so if you go to your formula sheet, to make a confidence interval, remember it's statistic plus or minus critical value times standard deviation of the statistic. Well, our statistic, we got two of them, and we're subtracting them, x bar sub 1 minus x bar sub 2, or what letters did I use? I used, let's see, C and N, but anyway, then our critical value is now going to be a t star, okay? We got to talk about that. All right, and then standard deviation of the statistic is going to be this guy here. We'll never use this, by the way. The special case where sigma 1 is equal to sigma 2, and that's not a part of the AP Stats curriculum. I don't know why it's on the formula sheet, but anyway, but just pretend like it's not there. So that is the one we're using in this section, which we demonstrated when we did our sampling distribution thing. So our statistic, and there's actually two of them, it's going to be x bar sub c minus x bar sub n. We're estimating, in essence, the difference. All right, plus or minus, our critical value is t star. All right, and then this would be s sub c squared over n sub c, and then plus s sub n squared over n sub n for no chemical plant. And so that is our formula. We have to use S in place of sigma because that's what we got. And it's for that reason that we have to use T star instead of Z star. If we knew sigma, we could use Z star there. But we're using T star because we have not only estimates here, but estimates there. Because we have so many more estimates, we have more variability. But anyway, and so this would, when we plug in these values that were given to us, so this would be 124 minus 106 plus or minus. Now, let's find what our T star is. And so, the next thing is this. Which T distribution are we working with? Because you go to your T distribution critical values, we have to know the degrees of freedom to know which of these rows to use, because each of these rows is a different T distribution. Okay, so we have to determine degrees of freedom. Remember last time it was the sample size minus 1. Well, we got two sample sizes. So there's actually with two sample stuff, there's a really complicated formula for degrees of freedom that you don't have to worry about. You can just use your calculator like I'm fixing to show you to get your actual degrees of freedom. But our estimate is going to be the smaller sample size minus 1, which in this case, the smaller sample size is 50. Both the sample sizes are 50, but you would use that as an estimate, okay? But you're really going to use the value you get off your calculator. And so you would go here and you'd say 95%, and so you would go up to 49 degrees of freedom, So you go to 95%. So you just go to we have 49 degrees of freedom, so you would just go to the closest 150. And so going up from 95%, there's 50. So it's 2.099. Anyway, and so that would be our estimate, 2.009. And then this would be the square root of, and so I enter in these values, and so this would be 14 squared over 50 plus 21 squared over 50, okay? And so this would end up being, 18 plus or minus about 7.096. Now, I ended up getting that off of my calculator like I'm fixing to show you because I did some rounding estimating here. And so this would be, in essence, 10.904 to 25.096. So that is using the formula. Now, no, you don't have to do that formula. You can just get this off your calculator. But you do need to understand what's going on here to be able to create this formula using your formula sheet. To understand that's the critical value. This thing here, the square root of all this, that's the standard error. That's the average amount our differences are going to vary from the middle of the differences. Okay? And then those two things together, that times that, that's what we call a margin of error. That's what that is. How far the interval's going to the left and to the right. And so, but let me show you how to do this with your calculator. So with your calculator, what you would do is you would say this. You would go stat, test, and this is a 2-sample t interval. So I go down here, and it's going to be the 10th option right there, 2-sample t interval. So we are starting to accumulate a lot of these things, 2-sample t interval. So I'm using stats because I'm given the stats, and so I hit enter. And so now my x bar sub 1 is 124, okay? And then my first standard deviation is 14, and the sample size is 50. Then my second sample is 106. Standard deviation is 21, and this is 50. My confidence level is 0.95. We never use pooled. So always say no to pool. Whenever your calculator asks you to use pooled, you always hit no to it. Now we do that pooled p hat as a calculation in the last section, but that's a different thing. We don't do it with the calculator. So we hit calculate, and that gives us our interval right there, 10.904, so to right there. And so that gives us that, okay? And so notice, before I do the ending, do you see that degrees of freedom? That is actually a more accurate calculation that your calculator does with degrees of freedom using a complicated formula that's in your book that is not in the AP Stats curriculum. So that is the actual degrees of freedom. We use this estimate of sample size if minus 1 when we don't have access to a calculator. So that is the estimate we use for it, is the smaller sample size minus 1. But this is actually a more accurate degrees of freedom. And all degrees of freedom do, they identify which t-distribution you're working with. Okay, and so lastly, let's do our ending, which is very similar to what we've done before. We were 95% confident, so you'd say I am 95% confident. I am 95% confident that this interval, and that would be 10.904, and what are my units here? Actually, I keep telling y'all it's important to include your units. And so this is and so 50 ounces of water, parts per million. It's mercury in parts per million, so include parts per million. Parts per million. That'll give you a little tick mark if you don't do that. Wouldn't necessarily make it go down from a P to an E or something like that, but give you a tick mark. If you get enough tick mark, they'll mark you down. So parts per million, include the units. Okay, that this interval captures the true difference of the population proportions. But I got to say what they are. The population mean, sorry. The true difference in the mean amount of mercury in the chemical plant river, minus the mean amount of mercury in the non-chemical plant river. Maybe not the best terminology in the world, but so that's what you got to say. You have to say it in context. You're 95% confident that the difference in proportions is in there. Remember, in the means. Remember, in Chapter 8, we would say, I'm 95% confident the parameter's in there, but you say what the parameter is. Now we're saying we're 95% confident that the difference in the parameters is in there because we got two of them. And so there we go. All right. Now, in regards to number 2, so then the next question that it asks on this thing is to perform a test of significance. to see if there's significantly more mercury in the river next to the chemical plant. Okay, so now we're going to perform, so this, what we just did was a 2-sample t interval. Now we're going to do a 2-sample t test, which is the other thing that you have to understand how to do in this section. Well, let's look at this interval. I mean, does it look like there's a significant difference? Well, I would say so. I mean, because 0 is not in the interval. Okay, these are the plausible values for the difference. So since 0 is not in the interval, it's not a plausible value. In other words, there appears to be more mercury in the river in general if it has a chemical plant than it doesn't, which sort of makes intuitive sense. All right, but this appears to be a big difference because 0 is not in the interval. But we're going to do the test. Now, we don't have to do the assumption, so we'll do the rest of this thing. So we have to follow the THAME acronym. So our type of inference is, this is going to be a 2-sample, so this is a 2-sample t-test for the difference in means. Okay, now we do the next thing, the H of our THAME acronym, and that's our hypotheses. Our null hypothesis is just going to be that the two means are the same. The mean for the chemical plant mercury is equal, well, the mean amount of mercury from the river with the chemical plant is equal to the mean of the river that does not have a chemical plant. Okay, the alternative. Let's see, which did it say significantly more? Notice it said significantly more in the river next to the chemical plant. Well, that would mean that mu sub c is greater than mu sub n. So the null hypothesis is always going to be that they're equal. The alternative is what you suspect might be true. Now, you're not allowed to look at the sample values and to say that's more than that, therefore I'll go greater than. It has to be something that's brought out in the stem of the problem. Okay, so it's that. Of course, you have to define this. Mu sub c is equal to the mean amount of mercury in the river with the chemical plant. And then mu sub n, you can use ditto marks here, mean amount of mercury in the river without the chemical plant. Okay, like that. We've already done the assumptions. They're the exact thing as this. So they would be that. In essence, there's no difference there. And so now we do our mechanics. So in regards to our mechanics, of course, we need a test statistic p-value. So we'll do our test statistic. So we go to our formula sheet. Remember, test statistic is statistic minus parameter over standard deviation of the statistic. Well, we got two statistics and we're subtracting them. And so that's going to be the subtraction of our two x bars, x bar sub c minus x bar sub n. So what the heck, we'll write this out. So this is z is equal to x bar sub c minus x bar sub n. That is our statistic difference. Our parameter, if we subtract that, that's mu sub c minus mu sub n. Well, guess what? Those two things, we're doing this hypothesis test assuming the null is true. Assuming the null is true, this thing's going to be 0. So that's 0, we're just going to erase it. Okay? Because the whole reasoning of this is if we assume the null is true, if we assume these two means are equal, what's the probability we're going to get sample values as unusual as these? And so that's what we're doing. And then over our standard deviation of our statistic, which, as we talked about, is that thing right there, standard deviation of our statistic. So it would be the square root of, and we don't have sigma, so we have to use s in its place. So it's s sub c squared over n sub c plus s sub n squared over n sub n, like that, just like what we did up there in essence. When you do that, when you calculate all that, plugging in those values, you would get that this is about 5 and this is good Lord, this is a t, not a z. Sorry, that's why we call it a t-test. I apologize for that error. That is a t. Good Lord. We can't use z because we're using estimates for both x bar and s are estimates. But anyway, so this is 5.0 0.04299. We have to write down our degrees of freedom, which once again we get off our calculator. So our degrees of freedom is 85.37. If we don't have access to that, we use the smaller sample size -1 as we have discovered. And we could use TCDF to find our p-value, but I'm just going to go ahead and show you how to use your calculator to do this. So you'll do stat, test, and this is a 2-sample t-test. There it is, the fourth option. So that's the other option, the fourth of our 4 options for this chapter, 2-sample t-test. We're using stats, and I just made the interval, so it automatically entered the stats for me, and I entered there, X bar, S. For data, like the next example we're going to do, we're entering data in a list. But so it's got all that. My alternative is greater than, so I got to go greater than there. And then we do calculate, and sure enough, we've got very dramatic. So there's my test statistic, T, and then my p-value is very small. This p-value is 1.27 times 10 to the -6. Write it like that. And so, or you could, and make sure you write p-value, not p. Don't write p like it says there, write p-value. And so that would be 0.000050127. And what that is in essence telling you, this is very unlikely to have a difference this big due to sampling variability. So this is in essence measuring how far is 124 from 106. This is telling us it's 5 standard errors, which is way off the chart actually. I mean, anything beyond 3 is really different, and this is 5. This is really unlikely to happen just by chance. And so if you were to ask to interpret this p-value, you would say, well, if the null is true, if there is no difference in these means, the probability we would get means as different as 124 and 106, 18 of 1, is way less than 1%. So that would give us reason to reject the null. So that's what we would do. So this is our same thing. This p-value, and you say what it is, 0.0234517, is less than 0.05 or any reasonable value for alpha. Thus, I reject the null hypothesis. Thus, I have convincing evidence that, and then you restate the alternative. I have convincing evidence that the mean amount of mercury, and I won't write all of it out, but yes, you have to write all of it out, and I'm sorry. The mean amount of mercury in the river, the chemical plant, is greater than the mean amount of mercury in the river without the chemical plant. And so that's how you do that. And once again, making the connection between the interval and the test. This p-value is really low, and so we would reject the null hypothesis. And the null hypothesis value is effectively 0. And 0 is not in the interval. Okay? Now, this is a one-sided test, which means for a 95% confidence interval, it goes with an alpha of 0.05, but with a one-sided test, it'd be 0.025. So because 0 is not in the interval, we're expecting our p-value to be below 0.025, and it certainly is. The other way of writing this, by the way, that you'll see in your book is this, the null hypothesis, and it'll subtract mu sub n from both sides. So it'll be mu sub c minus mu sub n is equal to 0, and your alternative being mu sub c minus mu sub n is, in this case, greater than 0. So sometimes you'll see it written like that. But, the key thing in that third question was, is 0 in the interval? It's not in the interval, and so it should be rejected. And that's exactly what we did. All right, and then this last problem here is a very similar thing, but they give us the data this time. You'll recall this from the past couple of chapters. In regards to quantitative data, in regards to means, they have one of two things. They can either give you the stats, like in this one, in this first problem, they gave us the stats, the X bar, the S, and the N. Okay, this one, they didn't give us that. They gave us the data in list form. And so we would, you could certainly find the mean of these numbers, which you've been doing your whole life, finding the average numbers, and now you can find the standard deviation. The sample size is certainly easy to find. There's 12 in each sample, so there's your n. So, we'll use our calculator in essence to do this. And, it's very, very similar to the exact problem that we just did. But anyway, so let's look at this problem, except that it gives us the data. So I wanted to do one like this. And so it says, a test is used to measure the math proficiency of 8th grade students. A researcher wishes to estimate the difference, the difference between the mean test score, not a proportion, it's a mean, so that's T, at Central Middle School and the mean test score at West Middle School. The researcher takes an SRS of 12. SRS makes us happy. 12, not so much, because it's less than 30. Of the 8th grade students at Central and another SRS of 12 8th grade students at West. So we can generalize. And because they've taken from the 8th graders at Central and the 8th graders at West, those are the ones we can generalize about. We can't generalize about the 7th graders. We can't generalize about other middle schools. We can only generalize about Central Middle School and West Middle School 8th graders, or people that we have reason to believe are like these. But anyway, all right, so it says to perform a test of significance to see if there's a significant difference in means, then to calculate the interval and to make, the connection between the two. And notice it said difference. It didn't say, well, we suspect Central should score higher than West or should score lower. That would lead us to a greater than or less than our alternative. But we have difference, and so that's going to be a not equal to. So let's do this problem. And so let's see if I can leave this here and then write down below there. Maybe, I don't know, but hopefully you've seen that. All right, so we're doing the hypothesis test, and so our type of interval, I'm not going to write this out completely because we just did that in that other problem. So our type of inference, so this would be a two-sample t-test for means, or for the difference in means. Our hypothesis is certainly important to do. So our null hypothesis is going to be mu. Never put X bar here. It's going to be the mean for Central is equal to the mean test score for West. And the alternative is going to be that the mean for Central is not equal to, because we have no hint for greater than or less than. You would then define, the other way this could be written, as we've talked about, minus mu sub W is equal to 0, or the alternative mu sub C minus mu sub W is not equal to 0, like that. And you would define, at this point, mu sub C is equal to the mean, the mean score for Central, and you would write all that. I won't go to the trouble right now of writing all that, but you have to when you do these problems. The mean test score for Central, the mean test score for West. Our assumptions, once again, like we talked about, are I sin. So, you would say, it is I sin. So you would say, it says SRS is 2 of them. Don't just say SRS. It says SRSs were taken, thus independent random condition is met. And so that's what you would write there. Independent simple random sample or independent random sample. Our population sizes, 2 of them, have to be at least 10 times our sample sizes. So you would say there has to be at least 120 students at each school. Now, let's talk about normality. With means, you've got 3 things. Is your sample size bigger than 30? No, it's not. So that would have established normality, but it doesn't. Does it say your populations vary approximately normally? No, it does not. So what you would have to do is you would have to graph your sample data, which I've done here. And as long as you don't have outliers or strong skewness, you'd feel good about normality. Now, at this point, hopefully you realize how this whole year is fitting together. Because what we did in August in Chapter 1, we learned how to make graph like this. This is a dot plot. Of course, we could also make a stem and leaf plot. We could make a box and whisker plot. We could make a histogram and that sort of thing. And we would cuss. We would say, oh, their centers are roughly the same. But this one has Central has more variability, but their centers are roughly the same. Which, by the way, leads me to believe that we're not going to reject the null hypothesis, right? But anyway, so we would cuss with that, and we would talk about how their spread and their shape, and both of these look to be pretty symmetrical. But the key thing here: do they have outliers or strong skewness? Certainly, West does not. Now, these 2 points here might be outliers. And you kind of have some liberty here, as long as you've made a good, honest effort. But t-distributions are pretty robust in regards to normality. So if you said, hey, there's a couple outliers, I don't feel good about normality, I think you're fine. Okay? But if you were to look at this and say, I don't think these are really outliers, and I don't think there's strong skewness, thus I feel good about normality. That's what you should say. And that's what I would say here. I would look at these sample graphs and I'd say, I don't see outliers or strong skewness, thus I feel good about normality. Then we have our mechanics. Of course, I went through this in-depthly in that last example, so I won't do it here. I'll just use the calculator with the data. So what we would do to get our mechanics here is we would enter the numbers in a list. So we go stat, we go edit, and I enter them in list 1 and list 2. Just like that, okay? And of course, I could make different graphs with this. Now what I'm going to do to get my test statistic p-value, I'll go stat, and I'll go test, and I'll go to 2-sample t-test. There you go. Stat test, 2-sample t-test. Now I'm entering data, because I entered data in list 1 and list 2. And so list 1 and list 2, my alternative is not equal to, so I go no. Always say no to pooled on your calculator. Now, the reason we would use pooled is if we had reason to believe our population standard deviations are the same, which we have no reason to believe that, okay? So, as a matter of fact, I don't think they are, because we have so much variability in the central middle school values relative to the West. But anyway, just always say no to that. That's the short answer. All right, so calculate. There's our test statistic and p-value. Wow. So our t-test statistic is equal to negative 0.2417 approximately. All right, and so then our p-value, so make sure and write p-value. Don't write what it says there, p. Write p-value is equal to 0.812. And there's your degrees of freedom. Now, of course, if we didn't have our calculator to estimate our degrees of freedom, we would use the smaller sample size -1, which would be 11 in this case. But that's all you have to write for your mechanics. You don't have to write your formula. So that's all you've got there. So this is a huge p-value. So notice it calculated the sample values for you. So the first one I entered was central. So central's mean was 72.45. And then West's mean was 73.3. And so what this is saying is, yeah, those are different, but they're not statistically significantly different. It is very plausible that those differences are due to sampling variability. Okay? And so Central may feel or West may feel all excited that they got higher in general, but it's not beyond sampling variability. If you were to take, samples of, 12 more kids on each school and do it again, it's very plausible that Central would score higher this time. They scored higher. They did not score statistically significantly higher, is what we're saying. But this p-value is extremely high. And so your ending, you would say this p-value, and you say what it is, just like what we've been doing for quite a while now, is greater than 0.05 or any alpha. Thus, I reject the null hypothesis. Thus, I do not have. Sorry, what I said that backwards. Sorry. Thus, I do not have. Yeah, be careful about that. I do not reject the null hypothesis. If the p-value is low, you reject the null. If it's high, you do not reject it. So make sure and be careful in that regard. Anyway, thus I do not have convincing evidence. Convincing evidence that, and you restate the null in context. And I'm not going to write it all out, but you've got to. You restate the alternative in context. So, thus, I do not have convincing evidence that mu sub c is not equal to mu sub w, but you have to write it all out. And I'm sorry you have to write it all out. I've fought against that, but I've lost. So, This p-value is greater than 0.05, thus I do not reject the null. Thus I do not have convincing evidence that the mean test score for Central is not equal to the mean test score from West. All right. Now, to make the confidence interval, and I won't go through, the assumptions or the name of it, the type of inference for the interval. And so that is going to be a two-sample T interval for means, just like we did, or the difference in means. Okay, and your assumptions would be the same as up there. Now, to make the interval, this is what you would do. Of course, we practiced this in our last example. You would go stat, test, and you go down to the 10th option, just like on that last example, except now, on the last example, we had stats, and we entered stats. But on this example, we have data. I entered data in list 1 and list 2. So we go that, 95%, always say no to pooled, and then we go, and there's our interval. Not surprisingly, 0 is in the interval, pretty close to the center, all right, because we have such a high p-value. And so this would be negative 7.974 to positive 6.3374. There's no units here, they're test scores, so we don't have to worry about that, but we ordinarily would. And so, we would say, so what you would say here in your ending, I'm 95% confident that the difference between mu sub c and mu sub w is in this interval. I'm 95% confident that this interval captures mu sub c minus mu sub w. Okay? And you say what those are. The mean test score on this test for all the students at Central minus the mean test score for all the students at West. Now, in making the connection between the interval and the p-value, remember our p-value is 0.812. Remember, our null hypothesis is that there's no difference. Mu sub c minus mu sub w is equal to 0. And so here's the connection. 0 is in the interval. Therefore, it is a plausible value and should not be rejected. This p-value, similarly, is a high p-value and did not reject the null. And so that's how that fits together. If 0 had been outside the interval, like if all of them had been positive, okay, and all of them negative, whatever, but if 0 is outside the interval, then it is not a plausible value, and it should be rejected, and we should get a low p-value. And so, as we've talked about before. Okay, that's it. That's 9.2, and thank you so much for paying attention. So I wish you much luck in two-sample stuff. I know that can be, a bit confusing, especially in regards to, those formulas, but you can do it, and you can be really successful. So I'll see you in class, hopefully, on time.